All right. So this is our part two of our wave particle duality lesson. The first part really talked about why the wave model of light broke down and then why the wave particle model was adopted. And the second part is really more about describing what that wave particle duality model looks like. Okay. So, um, when we create these models, remember models are only useful if they help us predict how something will behave in certain situations, like if we can predict how things work. So when our models break down, that means we have to discard them and replace them with new models. So the wave particle duality is really the model we adopted because we discovered that the particle model of light was incomplete and the wave model is also incomplete. So that meant we needed to create a new model. Um, and this model can get a little weird, right? It's a very counterintuitive. It seems that at the quantum level, quantum just means really, really, really tiny. At the quantum level, things don't seem to behave in a way that is intuitive for us. Okay. So, but we do tend to like, when we talk about a wave particle model, it's like, how can it be a wave and a particle? Like, that doesn't make sense. Or why is it behaving differently in like when we're observing it in different ways? And there's lots of different possible explanations for that. Um, and so right here, this is not really meant to answer those questions because we don't have answers to those questions. Go study physics if you want to answer them. But this is more just describing what this model looks like right now as we currently understand it. Okay. Um, so, first and foremost, light is actually a transverse wave. We haven't talked about that before, but sound was a longitudinal wave, at least when it's going through air. Light is a transverse wave. And the way we were able to figure this out was that we can filter out light um, depending on which way it's vibrating. Okay, so generally speaking, if you shine light through any light source or the sun, you can see here this little like snowflake looking thing. That's arrows pointing in every direction. So the light is vibrating in a random direction. Um, so you've got your little electric fields and magnetic fields that are going in every direction. But it's got a vertical component. And so I could create a filter that has basically solid lines through it, but it has holes in it, kind of like a picket fence kind of thing, that has holes in it. And that will allow the light that is going in the up and down direction to go through the filter. But anything that's vibrating in a different direction will get blocked, right? So if I have vertical slits, light that is vibrating in the vertical direction will get through. If I have horizontal slits, light vibrating in the vertical direction will not be able to get through and it will block that light. Um, this is actually how 3D glasses in movies work. Like if you take the 3D glasses off and you look at the movie screen, you'll see two images on the screen. And the reason for that is they basically have two images. One that is vibrating up and down. You need a special projector for this. One that's vibrating up and down. And then they'll have a second image that's vibrating left and right. And so the 3D glasses, what they do is it filters out one image for one eye. So one of your eyes will get one of the images on the screen, and your other eye will get the other image on the screen. And this is an artificial way to simulate 3D because that is actually how your eyes see. Is that each eye, because they're slightly in different positions on your face, will each see a slightly different image, and then your brain uses the difference between the two images to kind of construct that three-dimensional understanding of what's going on around you. So if you're blind in one eye, you don't have as much ability to see depth. You have to take other clues to figure out how far away things are. But that's how a 3D movie works as well, is that it's creating that illusion of there's two different images, and your brain uses those two different images to construct a 3D representation. Okay. Um, But light is a transverse wave that comes in indivisible pieces. Now, a sound wave, you can't do that. A sound wave, you can't cut it up into pieces. It's all, or it all comes sort of together. So indivisible pieces means that there's a piece of light, a certain size of light, we call it a photon, that you can't cut to be smaller, right? Like you always get at least this much light, and then every time you see light, you're getting multiples of that photon. So you can have a million photons, but you can't have, or you can have two photons, but you can't have half of a photon, right? So all of the light you see comes in those indivisible pieces. If light was a longitudinal wave, this filtering process wouldn't work. You wouldn't be able to filter it by direction. And if it came in, if you could cut it up however you wanted, things like the photoelectric effect wouldn't occur. Okay. Light is composed specifically of a vibrating electric field. Now, so usually light forms when you have an electron in an atom. So, like this electron, it gets extra energy somehow, and so it's at a higher energy state. And when that electron falls to a lower energy state, it kind of like moved a little bit, like it was vibrating for a minute. And when it vibrated, it created this vibrating electric field. And then the vibrating electric field creates a corresponding magnetic field, because magnetic fields are created by changing electric fields. Because it's a field, just like a gravitational field, the field itself has no mass. Like the object inside it can have mass, but like the source of gravity can have mass, but the gravitational field itself does not have mass. Okay, the light also is a field. It does not have charge either. Okay, but it does, because it's this sort of changing electric field, it can have lots of energy. Just like a gravitational field can store energy, this vibrating electric field can also store energy. Okay. Light does not need a medium, and that's because it is a field itself. Okay. And specifically that field is vibrating, but it is affected by mediums when it goes through them. So, like, remember we showed last time that refraction where it enters in this prism right here. So light is going in. We know that it's slowed down, because if it was traveling at the same speed, it would go in a straight line. But because it's entered in this, like, let's say it's glass, it might be something else. It could be plastic or something. But let's say it's glass. That tendency to bend is because it didn't get as far as it could have in the same amount of time. So it comes to bend, and then when it goes back out, it bends back the other direction. And that just shows that it is affected by the medium, so it does show some medium dependence, but it is able to travel without a medium. Okay. So getting back to that question, like, how can something be a particle and a wave at the same time? This is a video that explains what that might look like. This is not an exact, like, this is what it looks like. It's what a potential possibility could be. Okay.
Check this out. I'm using this speaker to vibrate a petri dish containing silicon oil. Now, if I take this toothpick and I make a little droplet on the surface, the droplet will stay there, hovering above the surface. The droplet is actually bouncing, and it'll keep bouncing for a very long time. Now, the reason for this is there's a little layer of air between the droplet and the surface, and the droplet's bouncing so rapidly that that layer never shrinks to about 100 nanometers, which is what it would take for the droplet to recombine with the oil. Now, every time the droplet lands on the surface, it creates a wave. But this is a special type of wave, driven by the vibration of the oil bath. It is a standing wave, meaning that it's not traveling out, it's just oscillating up and down. So the droplet makes the wave, and then it interacts with that wave on its next bounce. If the drop lands on one side of the wave, it is pushed forwards, and as long as the bounce of the droplet remains synchronized with the wave, it'll keep landing on the front side of the wave and getting pushed farther forwards. Droplets like these are known as walkers. The bouncing oil drops have been known about since the 1970s, but only recently has it been discovered that you can use these little droplets to replicate many of the strange phenomena of quantum mechanics. Now, obviously, this is not a quantum system. The droplets are about a millimeter in diameter, but you can think of the droplets like quantum particles, say electrons. One experiment that captures the key features of quantum mechanics is the double slit experiment. If you send a beam of electrons at two narrow slits, well, the electrons, rather than behaving like particles and ending up in two clumps behind the slits, they produce an interference pattern, even when you send each electron through one at a time. With walking droplets, the pilot wave goes through both slits, interfering with itself, while the droplet only goes through one slit. The droplet doesn't move in a straight line, though. It's deflected by its interaction with the wave. The resulting distribution of where the droplets end up looks very similar to quantum double-slit interference patterns. Or take tunneling.
He said the most important part of this video really, really fast. So I wanted to go over it again. Okay, so if you have a droplet that's creating a wave, now that wave is emanating out around that droplet. So that pilot wave is going to go through both slits, right? And because it reached over here and it kind of traveled through here. Now that means you're going to have two waves coming through here, and those two waves will interfere with each other. And then the little droplet, depending on which part of the wave it lands on, will go in a different direction. So this would kind of explain why, or it kind of can explain how it is possible for something that is a particle, like this little droplet, to behave more like a wave, because the wave is kind of what is driving the direction of where the particle goes. Now, in terms of applying this to light or even electrons, there's some flaws, right? Because we've, again, already disproved the existence of something like ether. So like this model kind of requires that you have a medium as well. And so we don't have like a working explanation for what that could be in terms of light. But it turns out these droplets are cool, and I'm gonna let the rest of this video play. Just in terms of, it shows off some other things that we see in quantum mechanics. Now, the rest of this video is not as important for what we're learning in this unit for quantum mechanics. Quantum mechanics is just how really small things move. And it will get into possibly some chemistry. But for those of you who are really into this, I'm gonna keep it going and kind of explain a little bit more at the very, very end. Okay.
Slit. The droplet doesn't move in a straight line, though. It's deflected by its interaction with the wave. The resulting distribution of where the droplets end up looks very similar to quantum double-slit interference patterns. Or take tunneling. In quantum mechanics, it's possible for a particle to get through a barrier that it wouldn't classically have enough energy to get over. This has been demonstrated with walkers by creating a shallow barrier under the surface of the oil. Usually the barrier reflects the pilot wave and its bouncing droplet, but in rare cases the droplet does cross the boundary. And the probability of the droplet crossing the barrier decreases exponentially with the increasing width of the barrier, just as in quantum tunneling. Perhaps the most surprising thing about these walkers is they exhibit quantization, just like electrons bound to atoms. Here the walker is confined to a circular corral. The droplet seems to move around randomly as it interacts with its pilot wave. The complex interaction between the droplet and the wave leads to chaotic motion of the droplet. But over time,
chaotic motion just means that it is unpredictable where it will go. Fun fact: was figured out by a scientist named Robert Brown and is sometimes called Brownian motion, and that is actually what my YouTube channel is named after.
a pattern builds up. This is the probability density of finding the droplet at any point within the corral, and it looks very similar to the probability density of electrons confined in a quantum corral.
So just a little bit of review from chemistry. This is like your S1, S2 like orbitals kind of thing. So it's like, where are you going to find the electron when it's orbiting around the nucleus? And so, like, again, just through the random motion of this water droplet, you get a probability distribution that's very similar. What's interesting to me about this is that it's not that it's impossible for the droplet to be between the two energy levels. It's just it's way more likely to be at those particular valence locations, right? So, same thing with an electron. It's not maybe completely impossible for it to be in between. It's just that it always shows up there. And when we're talking about this, we don't really ever observe electrons in between. Um, so it does seem to exhibit like it's at this place, or it's at this place, or it's at this place. But this could suggest a possibility for how the mechanics of that might work.
All of these similarities are no coincidence. The walking droplets actually create a remarkable physical realization of a theory proposed by de Broglie nearly 100 years ago in the early days of quantum mechanics. He postulated that all particles have a wave that accompanies them and guides their motion, and that wave is actually created by tiny oscillations of the particle. Now, this pilot wave theory was marginalized when the standard Copenhagen interpretation became widely adopted. The Copenhagen interpretation excludes anything that cannot be directly observed, and it says everything that can be known about a particle is contained in its so-called wave function. But adopting this view forces you to give up on some common sense notions, like the idea that particles have a definite position and momentum even when they're not being measured. And it also meant that the universe was no longer deterministic. Randomness is built into standard quantum mechanics. For example, take the double slit experiment. According to quantum mechanics, the wave function of the electron is a superposition of the electron going through one slit and the other slit simultaneously. Using this wave function, you can calculate the probability of where the electron is likely to be. And then when you detect it at the screen, the electron pops up at one point at random that was in that distribution. We say that its wave function collapses instantaneously at the moment of measurement. You can't say that the electron was there before you measured it, and you can't even say that the electron must have gone through one slit or the other. Compare that with the picture provided by the bouncing droplets. In this case, the pilot wave goes through both slits, but the droplet only goes through one. The droplet is pushed around by its interaction with the wave so that the resulting statistical distribution is the same. The droplet never exists in two places at once, and there's no randomness. If there is any uncertainty, it's just due to our ignorance of what's going on. It's not that it doesn't exist. So pilot wave dynamics can produce many of the same results as quantum mechanics. Does this mean that this is really what quantum particles are doing? No. But I think it'll at least suggest that this is possible. These are possible dynamics that could lead to the statistics which are captured in the quantum mechanical theory. And what's appealing about this is it gives you a clear idea of what's going on. You don't have to abandon the idea that the universe is deterministic, and you get particles with definite position and momenta. I think it's
Um, he thinks it's great that we have competing theories, and that's a very important part of science. Absolutely. Um, so that again is an example of what something being a wave and a particle at the same time might look like. Again, we don't. There are problems with that explanation as well, as I mentioned before. So when as you're going through this, just keep that in mind. Quantum mechanics is very successful in how what it predicts in its experiments. And Einstein's theory of relativity and general relativity specifically, which is about gravity, is also really successful. And what science is really trying to do right now is find what physics is really trying to do right now is find a unifying theory that allows that can kind of explain the effects and phenomena we've seen in both realms, um, because that would just make everything simpler to understand potentially, but you never know. Anyway, that is all we're going to talk about with wave particle duality. for the purposes of this unit. I will see you next week.